Hello, this is the first video of a preliminary series on sets, permutations and combinations for the OCR AS Discrete Further Maths. This video covers the types of problem you may encounter. Discrete maths is the branch of mathematics dealing with objects that can assume only distinct separated values, such as integers that are counted. In contrast, continuous mathematics deals with objects that can take any value, such as real numbers, that are measured. One area of study in discrete maths, known as combinatorics, looks at how discrete objects combine with one another to give various outcomes. Other examples of discrete mathematics topics are the study of algorithms, graph theory and its applications to networks, and decision-making processes such as game theory. Discrete maths is hugely important in computer science and thus is vital in the modern world. There may be several approaches to solving different types of problems. Depending on the nature of a problem and the solution techniques available, more than one of these approaches may lead to a useful or successful outcome. It is often useful to think carefully about the type of problem that you're being asked to solve at the outset. In combinatorics, problems can generally be categorized into four types: existence, construction, enumeration, or optimization. So, an existence problem asks, does whatever exist? A construction problem asks, if whatever exists, how can we construct it? An enumeration problem is of the type, how many of whatever are there? Optimization asks which of whatever is the best according to some criteria laid down. So, for example, if we wish to travel between two locations, we might ask, does a suitable route or direct route exist, which would be then an existence problem. If so, can we construct or find one with perhaps some changes between transport types? That would be a construction problem. How many routes are there? An enumeration problem. Or, for an optimization question, we might say which route is best in terms of the shortest time or lowest cost or type of transport. Let's look at another example. If I wanted to write a list of integers containing 2 square numbers, 2 prime numbers and 2 cube numbers, I might phrase this as an existence problem. Does a list of 2 square numbers, 2 prime numbers and 2 cube numbers exist? Or a construction problem. How can I construct a list of 2 square numbers, 2 prime numbers and 2 cube numbers? Or as a enumeration problem, how many lists are there containing 2 square numbers, 2 prime numbers and 2 cube numbers? Or an optimization problem, such as what is the minimum number of integers that could be in my list? For the existence problem, we may find that the solution could be by a statement of proof or could be by stating a valid solution to the problem. By proof is possible because we can show that at least 2 of each type of number exists by stating them. For example, we know that some square numbers include 1, 4, 9, 16, 25 and so on, from which we can choose 2. The same with prime numbers. 2, 3, 5, 7, 11 and so on. And also with the cubes 1, 8, 27, 64. So from these we can just choose 2 of each and therefore we have proved that a list exists. For the construction problem, the solution could be as simple as a set of instructions to construct a list. For example, instructions might be write down 2 square numbers, 2 prime and 2 cube numbers. Algorithms, a topic we will consider later in the course, might be used to solve construction problems. Considering the enumeration problem. Enumeration broadly means to list or to count, so we often have either counting problems or listing problems. We might even list things in order to count them. For the above example problem, we cannot do a complete enumeration. Sometimes listing all the solutions is not practical, but we can still count how many there are. Here we cannot do either, as we are dealing with an infinite set such as integers. However, if we impose a constraint on the problem by setting an extra condition, for example, the question becomes, how many lists are there containing 2 square numbers, 2 prime numbers and 2 cube numbers with all the numbers being less than 10, then we may well be able to solve the problem by simply listing. So then, if we consider the possibilities, the square numbers 1, 4 and 9 are less than 10. The primes 2, 3, 5 and 7 are less than 10. And for the cubes, we know that 1 and 8 are less than 10. So these are the only choices we have for the square, prime and cube numbers if all the numbers are less than 10. Let's have a look then and think about how we could count the lists we can make. Well, for the 2 cube numbers we don't have any choice, so we know we're going to have a 1 and an 8 in the list. Looking at the squares, we could, for example, choose the 1 and the 4. However, we wouldn't need to repeat the 1. And then for the primes, we could choose the first 2, 2 and 3, and that would be a list that met the conditions. However, for the primes, we could have chosen, say, 2 and 5 instead, or 2 and 7. Or we could have chosen, for the last 2 digits, we could have chosen 3 and 5, 3 and 7, or indeed 5 and 7. So you can see that there would be 6 options for the primes if we chose 1, 8, 4 as the square and cube numbers. So as this is a counting problem, we can go about it by starting to list solutions in a systematic way so that we can work out how many more there are without necessarily listing them all. Moving on then, for each pairing of square numbers, we know we all have 6 lists, and there are 3 different ways that we can choose for 2 square numbers, i.e. the 1 and the 4, the 1 and the 9, or the 4 and the 9. So the total number of lists must be 3 times 6, 18. This is an example of a multiplicative law. This law is used when a counting problem can be split into distinct stages, and we can count the number of options at each stage and then multiply. Moving on to look at the optimization problem. Optimization involves looking for the best solution to satisfy some given criteria, and many optimization problems involve maximizing or minimizing some quantity. We can't enumerate the above example problem, so we use logical arguments. We've already seen lists with 6 or 5 elements, but could we have fewer? Well, considering the lists of cubes, 1, 8, 27, 64 and so on, and then of squares and then of primes, we will note or remember that prime numbers have exactly 2 factors. Square numbers have 3 or more factors, as do cube numbers. So if we find square and cube numbers that are the same, then we could reduce the length of the list. Let's have a look and see if we can. Well, we can see from these lists immediately that 1 and 64 are both cube and square. So if we use those in the list and then 2 primes of our choice, we would have had a list of 4, and thus we can say that the minimum number of integers that could be in my list must be 4. One example of that being 1, 64, 2 and 3. Here we have a more complex but interesting problem to tackle for yourselves. So in the grid below there are 4 numbers A, B, C and D. The numbers in the first column are fixed and should be chosen so that in the entire table the total number of 1s is A, the total number of 2s is B, the total number of 3s is C and the total number of 4s is D. We can see here that there is one incorrect solution. It is incorrect because, although we have said that there are 2 1s, in fact if you look at the table there are 3 1s in the table, so A cannot be 2, it should be 3, and so on. The 2 questions are 1, an existence problem, can you find a solution to this problem? And then an enumeration problem, or how many solutions are there to this problem? You can see that this problem is taken from the NRICH website, which we recommend as a great place to find problems to try. You may wish to pause and have a go at this for yourselves, either now or later, and then check the solutions. The type of reasoning you might use runs a little bit like this. You cannot, for example, have A equal to 1, as then there would be 2 1s in the table, and so therefore A would have to be at least 2. We could try A equals 2. If A was 2, then B could obviously not equal 1, because there would be at least 2 2s in the table. You could try B equals 3. In that case, you might get away with C equals 2 and then D equals 1. In the next video, 1.2, we cover the pigeonhole principle.